Hello everyone, this is Puya. This lecture is about numerical integration and differentiation. So let's first look at numerical modeling. Some systems models will be given as implicit functions or as differential equation. These can be solved either using analytical methods or numerical methods. So for example, we have a mechanical equation here, right? That would basically determine the behavior of velocity versus the acceleration that we have. There have some constants here, and this basically, in order to find the behavior of the velocity versus time, we have to solve this equation. So like in this equation, like the changing velocity is determined by the gravitational force acting on the jumper versus the drag force, right? So that's basically showing a system being modeled as a dynamic equation, right? To solve this problem, we either have to solve it uh, like using analytical methods, or we can solve it numerically, right? So like sometimes, like in order to solve the system, we can't find an analytical method. We will see like some cases why we can't find the analytical method, like either we don't actually have the function itself, right, to take derivative of, right? Or like maybe it would be very difficult and time consuming to do it exactly using analytical methods. So numerical methods provide some approximation, right, for derivation, for integration, finding the roots, like many different mathematical techniques that we have to apply on the problem. So in this case, if we want to find the derivative of the velocity, one way of doing it is using a numerical method. And so by doing so, then we can just basically, if we have samples of the velocity, we can actually find the velocity at a future time sample. Okay. We can also like solve the system analytically, like finding the exact solution, right? It would be maybe more like we would need to like put more effort to do that, and sometimes it's not possible to find the exact analytical solution, and the approximate numerical solution in most cases it can be providing a very good approximation, like if we apply the correct numerical method that would generate not a significant error amount of error. Okay, and if you want to make this numerical approximation more precise and more accurate, we can just reduce the time step, right? So like instead of having a wider time sample, we can just reduce the step size, right? By doing so, we can get closer to the exact analytical solution. So some of the numerical methods that we have is to find roots or find the optimum points of a function. So we can also like solve numerical algebraic equations, linear equations. We've seen that before. We can do curve fitting. We're basically doing regression or interpolation. And like what we're going to see in this lecture would be numerical integration and differentiation. So if we want to solve this integral, right, it's a definite integral, like we have to, we're taking integral of this function from point A to point B. This integral represents the area below the curve, right? So like we basically want to find this area. So all the numerical integration methods that we have are different ways of approximating this this area, right? So like what we're gonna try to solve would be integral over certain boundaries, right? So like it's a definite integral, and we're just gonna find a good approximation for the area below the curve. That's the whole concept of numerical integration. So let's start with an example. Let's say like we want to find the integral of this function sine of x from 0.0 to pi over 2, right? This is very easy to calculate exactly analytically, right? So because we know the antiderivative of sine is negative cosine, right? So we can just like solve this exactly and find the exact analytical solution. In this example, the reason we could do it so easily was because the antiderivative is easy to calculate. In many cases, it might not be the case. Like it might not be very easy to calculate the antiderivative. Also, we might not even have the function that we need to integrate. We might have like some sample data points, right? So we don't even have a function to take the antiderivative of, right? So in these cases, like these are two scenarios that we want to apply numerical integration methods, right? So there are certain formulas like Newton formulas that are the most common numerical integration schemes. It basically tries to find an approximate function that we know how to find the integral of over the interval that we have to take the integral of, right? So this is basically the whole point of numerical integration, approximating the original function with another function, right? So there are many different options for this approximate function that we want to find, and we'll see like all of it or most of it in this lecture. So here you see some of the techniques that we can apply to find a numerical approximation for area below the curve, right? So one way of doing it is just like basically approximating this function between a to b with just a straight line. And instead of finding the area below this curve, we want to find the area below this straight line. Okay, so that's one way of approximation. Another way of approximating would be just approximating this function, again, like from point A to point B with a quadratic curve, right? With a quadratic curve, right? And in that case, again, like because like this is a polynomial, we know how to find the antiderivative of polynomial. It's very easy to calculate. So again, like we can easily find the area below this curve. In this case, you will see that like this method is going to be more for this specific example. This method, it's more accurate than this one because here we have this much error. The error that we have here, it's basically this area, this extra area minus the empty area here. Okay, another way of doing it is just like using piecewise approximation or applying composite rules. So basically decomposing our interval into smaller intervals, and like in this case we are just gonna connect each 2 points of the two ends of the interval with a line, with a straight line. And instead of finding the area below this blue curve, we find the area below these lines, straight lines. Again, because this is a straight line, we can actually like if you think about it, this is a trapezoid, so we can actually find the area of a trapezoid very easily. Or we can just like, it's a polynomial, right? First order polynomial, so we can find the antiderivative of it and take the integral of. So these are some of the methods that we're gonna see in this lecture. Okay, so one easy approximation method that we can have, it would be just approximating our function with a constant function. It means like a horizontal line when f of x is a constant, right? So there are different methods for doing it, right? So like what constant should we use, right? This function changes all the time between a and b, right? So in one case, we can choose that function to be f of a, the value of the function at the starting point of the interval. Another method would be choosing b, right, f of b as the constant. So you see, like here, we are approximating this pink area with the area below this line, red line, right, the first red line. So like this smaller rectangle that we have here. Or we can approximate it using this bigger rectangle. So you can see, like, we can either like use f of a or use f of b. Another way of doing it would be just like finding the midpoint in the interval, which is like a plus b over 2, finding the value of the function at that midpoint, and then making the approximate function a constant function, which is equal to f of a plus b over 2. Okay, so these are different methods that we can apply, and this is the simplest function that we can use to approximate our original function for the sake of integration. So this is called rectangle rule, right? In the rectangle rule, we're just approximating our function that we're going to integral of with a constant. That constant can be either f of a, can be f of b, or more commonly used approximation would be finding the value of the function at the midpoint. And this is called midpoint rule, midpoint rectangle rule. So we are basically approximating f of x through the whole interval between a and b with this constant, which is f of a plus b over 2. This is called the midpoint rule, right? So like if this is a constant, it comes out of the integral, and this is going to be b minus a times that constant, right? Which is like basically the area of this pink rectangle. It's the height is f of a plus b over 2, and the width is b minus a. If we apply the midpoint rule to the function that we to the example that we did earlier on, which we calculated the area, the integral of sine of x dx from 0 to pi over 2, and we saw that the exact solution was equal to 1. If we apply the midpoint rule, right, so between 0 and pi over 2, the midpoint would be pi over 4, right? Sine of pi over 4, it's root 2 over 2, and this is going to be the width, which is pi over 2 minus 0. If we do the calculation, we find this numerical answer, which is 1.11, and you see that like it has 11%, almost 11% error compared to the exact solution, right? So this is the simplest approximation that we can have for numerical integration. The second rule that we can apply for numerical integration, it's called trapezoidal rule. So instead of having just a constant function, we approximate the original function within the interval from a to b with a line. Which line? The line that connects the two ends of the interval, right? So we find f of a, we find f of b, and we connect them, right? So we have the a, we have b, we can find f of a, we can find f of b. So this, we can find the equation of this line, the line equation, okay, which is given here, right? If we have 2 points of a line on a line, we can find its equation, right? If we take the integral of this one, it's going to be the area of this trapezoid, right? Which is going to be f of a plus f of b divided by 2 times b minus a, okay? So this is called trapezoidal rule, because we basically approximating the area below this curve with the area of this pink trapezoid. Okay, so you will see that this is not going to be exact. We have some error. So in this case, like the error, you see like we have huge amount of error, right? We're not counting this the area of this shape over here from below the blue curve up to the uh, top of this black line. Like this is not included in our approximation. So we have this much error, right? And in this case, again, like we have some error, like we are not considering this one and we are over approximating at this point, right? So again, like you see that like it has error. If we, let's say like if we want to take integral of this function from this point to this point, right? If our function behaves like this, if we apply just like the simple trapezoidal rule, would be just like connecting this point to this point and like only considering this area here, this area here, right? The area of this trapezoid here. And we have this huge amount of error, right? Which doesn't make sense, right? So like this is not it's gonna be a very exact or precise numerical method. So instead of that, in order to reduce the error of the trapezoidal rule, we can basically decompose our interval into smaller intervals, right? And apply the trapezoid rule for each smaller sub-interval, right? So here you see that our interval is broken into 6 smaller intervals, sub-intervals, and for each sub-interval we are applying the trapezoid rule. Okay, this is called composite trapezoid rule. So, and it definitely reduces the amount of error. Now, like in this case, we have this much error for this sub-interval. Like here, like we are over approximating this much. This is like almost okay. Like this one, like we are not considering this area. You're not considering this area, and so on. How many sub-intervals? Like the more sub-intervals we have, like our method becomes more accurate, but like you also like have to do more calculations. So like it's basically a trade-off, a trading between the complexity versus precision. Like this is like usually the case. The effort that you have to put into calculating versus accuracy or precision. Okay, so here you see an example of a problem that we have to apply numerical integration. We have an accelerometer, right, is used in aircrafts, right? Like so the accelerometer integrates acceleration signal to produce an estimate of the velocity. We have the acceleration data points. We want to find the velocity, right? We know that based on our physics knowledge, we know that in order to find velocity, we have to take integral of acceleration over time, right? But what is the function of acceleration? We don't have any function to take integral of, right? So we only have some data points, right? We only have some data points. So like there is no way that we can solve this exactly because we don't have the exact function for the acceleration. So we have to estimate the velocity. You have to estimate the velocity. So in this case, we have some data points, right? You have some data points. In part A, it's asking you to estimate velocity after 10 seconds. After 10 seconds. If you want to use a simple trapezoid rule, which is going to be very erroneous, like it would have a very low degree of precision, right? We can just like use the data points at the beginning of the interval, at the end of the interval, right? And like find the line that connects them and find the area below that trapezoid. But this is not going to be very accurate. Instead of doing that, we can just like do what we had here. We have 11 data points, right? 11 data points. So we can have 10 sub intervals. We can have 10 subintervals, and for each of them we can calculate the area below the curve, the area below the curve. So basically 10 trapezoids to find the area of, and once we do that, then we just like add all those areas and we have the answer. And if we apply the composite trapezoid rule, another advantage of that is like finding like the integral, or like in the case of this example, velocity at middle points as well, right? So like we would have the velocity at this point, at this point, at this point, at this point, and so on. If we just like apply a simple trapezoid rule, we only find the integral from this point up to this point, right? But if we do composite, right, we can find the integral from here to here, from here to here, and so on. So you can work on this. The answer, the final answer is given here, right? So you can double check your answers versus this one. But basically it's like calculating the areas of these trapezoids that we have. And just remember that sometimes the trapezoid might reduce to a triangle. So for example, in this case, where acceleration at the beginning is 0, right? So like imagine if this was at 0, right? This trapezoid would be just like would reduce to a rectangle. Okay, so just keep that in mind for the first subinterval that you have to find the area of. If or like this is actually like what I was talking about, right? So here, because sine of x at x equal to 0 is 0, right? If you want to apply the trapezoid rule, like it would just like reduce to a rectangle, the area of a triangle, right? The area of a triangle. So if you apply the trapezoid rule to this problem, right, then the answer that we get is 0.78, right? The exact answer was 1, right? You see that like here we're not considering the area of this shape over here. That's the amount of error that we have, right? For this example, you saw that the midpoint rule was more accurate than the trapezoid rule. That's not always the case, right? That's not always the case. Usually trapezoid rule should be more accurate than the midpoint rule, right? This was just like a coincidence that like for this example, midpoint rule was more accurate. Because why would it be like more accurate? Because like we're actually using a more complex function, right? So like we are using more information about the function like this. One suggestion I have for you, right? Instead of using a simple trapezoid rule here, maybe you should like do it yourself, like find like maybe the midpoint rule, right? And apply composite trapezoid rule. So like one trapezoid from here from 0 to pi over 4 and another one from pi over 4 to pi over 2, right? That should make your rule much more precise, much more accurate. Okay. So this is what I was talking about, the composite trapezoid rule. Okay. So it would be basically instead of just finding the area of one big trapezoid, like we break the interval into smaller subintervals. Okay. And right, these subintervals are not necessarily the same size. Keep that in mind. They're not necessarily the same size. In many cases, for simplicity or like for making the calculations easier, we make it the same size, but they might not be the same size. Like let me look at this one. So for in this case, the intervals were uniformly broken, so they're the same size, but that's not the case. So here you see that, for example, the last subinterval is much bigger than the previous ones, right? And you just basically have to add up the areas of each of these small trapezoids. Okay. If you want to make your calculation simpler, right, then you can use this formula, right? Right here we assume that we have the same step size, right? We assume that the step size is it's not shown properly, but like if we assume that the step size is the same um, for all the sub intervals, the step size is basically the width of this sub interval, right? Which is going to be b minus a over the number of sub intervals that we have. If h is the same, right, then you can use this formula to find the summation of all these areas, right? It would be h over 2 multiplied by f of x0 plus f of x and plus 2 times f of the midpoints, right? Anything it's in the middle, right? So these are the or like inner points. Let me call them inner points, right? These are terminal points, and like 2 times the summation of the inner points, like the function value at the inner points. Okay, uh, like you can actually see how this formula is derived based on the calculations given here. Okay, another method that we have for integration, it's a family of rules called Simpson's rule, right? So instead of approximating this function with a straight line over the interval from a to b, we can approximate it with higher order polynomial. We can either approximate it with a second order polynomial, which is going to be a quadratic function, or a third order polynomial, right? A third order polynomial. You remember that if we want to have a quadratic function, right, we need to have 3 points to find a quadratic curve uniquely. If you want to have a line, we only need 2 points, right? That's why, like in the trapezoid rule, we use the beginning and the end of the interval as the data points. If we want to have a quadratic function, we need to have 3 points, right? So we can use the 2 terminal data points and the middle one. Or like if you want to have a third order polynomial, right, a cubic curve, right, in that case we need to have 4 data points on the curve, right? So in that case we can find the cubic trapezoid or cubic curve that passes through these 4 data points, and because this is a polynomial, we can easily find the antiderivative. So you see that like this is, both of these are going to be more complicated than the trapezoid rule or the midpoint rule, but the accuracy is going to be higher, right? So as like also like we move to higher order approximation, the accuracy goes higher. So if we have 3 points on the function, right, we can find the quadratic curve that goes through those points uniquely, right? So this shows like how we can find them, right? The quadratic or the second order polynomial is going to be ax squared plus bx plus c, right? If we have 3 data points on the function, right, we basically have 3 equations, 3 unknowns. We can find the coefficients of that quadratic curve uniquely, right? And this formula basically shows you how to find those quadratic curves function, right? So that's, and if we take integral of this quadratic curve from point x0 to x2, right, this is like what we get as the answer. So you don't have to memorize any of this, right? You just like can use the formula, right? H is the step size, h divided by 3. So that's why this rule is called Simpson's rule, Simpson's 1/3 rule, right? This like h over 3. F of x0, right, which is going to be at f of x0, it's going to be this value. F of x2, it's going to be this value. And f of x1, it's going to be this value, right? So this would be an approximation for the area below the curve. This is called Simpson's 1/3 rule. Okay, if we apply the Simpson's 1/3 rule, right? So here, this is like, you see, this is f of a, this is f of b, and this is f of a plus b over 2. So exactly like what we had here, right? Our h here, like our h is like the distance between the two data points, right? So it's, our h is b minus a divided by 2, right? B minus a divided by 2, it's h, but we had also like a 1/3 in the function, right? In the answer. So like that's why it shows b minus a divided by 6, right? So that's what the Simpson's 1/3 rule is. And if we apply it for the same example that we did using midpoint rule and the trapezoidal rule, we see that for Simpson's 1/3 rule, right, it's just going to be b minus a divided by 6, which is going to be pi over 2 divided by 6. F of a is 0. F of pi over 2 is 1. And the midpoint, this midpoint is going to be pi over 4. Sine of pi over 4 is root 2 divided by 2. It has a coefficient 4, so that's why we have what we have here. And you see like what the answer is, right? It's pretty accurate. The error that we have, the exact answer, if you remember, it was 1. The numerical approximate answer is 1.0023. Okay, so it's basically the error that we have is 0.23%, which is pretty good. Which is pretty good. So you see that as, but like you have to do more calculation, right? You have to do more calculation. In the midpoint rule, we just had one. We had to find the value of the function at the midpoint. In the trapezoid rule, we had to find the value of the function at 2 points, right? The 2 terminal points. In the Simpson's 1/3 rule, we have to find the value of the function at 3 points. And in Simpson's 3/8 rule, like this one, we have to find the value of function at 4 points. And also, accordingly, our amount of calculations that we have to do increases. But so does our accuracy. Okay. Similar to what we had for trapezoidal rule, we can also have composite Simpson's 1/3 rule, right? So we can break our interval into smaller subintervals, right? So you see like here, this is this one, like 1, 4, 2, this is one subinterval, right? We need like 3 points, right? This is one subinterval. The other one would be going from this point up to this point. The other one from here to here, from here to here, from here to here, right? If we do that, again, our accuracy is going to increase, right? So like here, right, like we need to do more effort. We spend like more energy on this, right? We have to find the value of the function at more data points, but the benefit of that is our answer is going to have less error, right? And this shows you the excuse me, this shows you the formula for the composite Simpson's 1/3 rule. Remember that h is the distance between two adjacent data points. So like h is going to be this one in this case, this value, right? Okay. We could also have composite midpoint rule, right? So for any of the rules that we saw, midpoint rule, trapezoidal rule, Simpson's 1/3 rule, even like Simpson's 3/8 rule, we can do that compositely. Like what does that mean? It means like breaking the interval into smaller subintervals and applying the rule on that smaller subinterval. This shows you an example of composite trapezoid rule, right? Trapezoid rule, like so here you see that like how it's applied on this function, right? So this is composite trapezoid rule. For like midpoint rule or for Simpson's rule, it's the same thing. This is like composite Simpson's rule, right? So this is one interval, this is another one, this is another one, this is another one, this is another one, and so on. Okay. The Simpson's 3/8 rule, it basically uses a cubic polynomial to approximate the function over the interval that we have, right? And the formula for that, right, we can, like, if we have 4 data points on the function, we can find the formula for the third order polynomial, a cubic polynomial that goes through those 4 data points, and we can approximate the integral with the integral of this polynomial. Like the middle calculations are not shown here, like this is the final result, right? So we have 4 data points, f of x0, f of x1, f of x2, and f of x3, and the area below this third order polynomial can be calculated like this. Sometimes you can let's say, like for this example, you see that here, like it's using 1/3 rule, Simpson's 1/3 rule on this part of the function, like on this interval, and 3/8 rule on the other part. So like we can just like mix them up, right? So we can mix them up as well. Simpson's 3/8 rule is generally used in concert with Simpson's 1/3 rule when the number of segments is odd, right? So here you see like 1, 2, 3, 4, 5 segments, right? So we use a 3/8 rule on this part and 1/3 rule here, or like you can just like use 3/8 here and 1/3 here. Okay. If you want to make your error smaller, right, you just like have to increase number of subintervals that you have, or it basically means like your h has to get smaller and smaller, right, so that you have more subintervals. As number of intervals increase, you see that the error is gonna go down, right? For trapezoidal rule, the error, it's gonna be of big O notation h squared. What does that mean? It means that if you make h 10 times smaller, your error gets almost 100 times smaller, right? But excuse me, for Simpson's rule, right, it's order of h raised to power 4. What does that mean? It means that, let's say, like if you make your h 10 times smaller, your error gets 10,000 times smaller. Okay, 10,000 times smaller, right? So that's another advantage of Simpson's rule. Okay, so this basically shows like how your like if this is your estimate, like if this is your exact answer, right? You see like how trapezoid rule or Simpson's rule like basically reach the exact value as the number of intervals increase. And for Simpson's rule, it's like pretty fast. The error is like very small, right? So you don't need to do much decomposition, right? But for trapezoid rule, because like it's a simpler approximating function, then you have to basically increase the number of subintervals to get to the same, you don't even get to the same accuracy as the Simpson's rule. This summarizes all the formulas that we saw like earlier for midpoint rule, for trapezoidal rule, and for Simpson's 1/3 rule. So the whole point, as like just like a sum up of what we've seen, like the whole point is approximating the definite integral with something that we call numerical quadrature. Like it's like something like instead of finding this integral, we are approximating f of x with another function, and we break it into smaller subintervals. Okay. So this is showing you like the composite rule, the trapezoidal rule, rectangle rule, midpoint rule, Simpson's 1/3 rule, and this is the composite Simpson's rule. In MATLAB, you can use the quad function to find the integral calculated using Simpson's rule, right? This one needs the function handle to do so and use the limits of the function. And this function traps, it's going to be applying trapezoidal rule on set of data points that you have. So let's look at like how they can be applied. So if you have data points, let's say like similar to the example that we did earlier on, this one, right? If you have the data points, like let's say this is our x and these are y's, and we want to find the integral, we can just like easily use the traps, right, to find the value of our integral, right? If we don't provide the x variable or the x vector, like it would just basically assume that the stepping is always 1, right? But if you have the x value, it just like finds the stepping based on your x values. If you want to like here, like if you apply this, it would only give you the value of the big integral, right? So like the integral from the beginning of the interval to the end of it. If you want to find all the mid values as well, all the inner values, right, then you want to use a cumulative trapezoidal function, right? So cumulative integral, like it would basically give you, let's say if I apply it like on this one, like it would, let me just like go to a, like here, right? It would give me the integral up to here, integral up to here, integral up to here, integral up to here. So it would give us all the mid values that might be also helpful to know, right? It provides some information. Although quad function is more accurate than traps, they are restricted to computing the integral of functions and cannot be used with the integrand as specified by a set of points. For such cases, we use traps function. So like if you have only data points, MATLAB, you use the traps function. This shows you an example of applying cumulative traps function on basically these data points. Like this is the example that we wanted to solve earlier on, or similar example that we wanted to solve. So this is going to give us the total integral, but this is going to give us like the integral values at like every single time step. Okay. So if you want to find the value of this integral from 0 to pi, right, we can find like have a vector x. So it's going to be a linear spaced vector between 0 to pi with 10 data points. Find y and then apply traps function, right? So that's it gives us like this value, which is like has like around 1% error. Or you can use the quad function. Sorry, I got like very excited. You can use the quad function. So here, for the quad function, you need a function handle, right? You need a function handle. So here we say add sign, and you need the limits of the integral from 0 to pi. So, and in this case, like the answer that we get is like almost like the exact answer that we expect. Okay, so here it shows like another example using the quad function, right? We want to get the integral of cosine of x squared from 0 to root 2 pi, right? So first we define our function, right? Cosine squared, right? And then you remember that like here, like we need to have like a dot operator here, right? It's just not just raised to power 2 because x can be a vector. And then we just apply the quad function, right? We call like our function handle is the name of our function, and we go from 0 to a square root of 2 pi. Another example similar to this one, like this shows you another example. Again, like we have a function, right? This time, like there's a function inside another function, right? One to define the function that we want to take the integral of, and the other one is to just apply the quad Simpson's 1/3 rule. You see another examples here, taking the integral of sine of x. This is like an example of trapezoidal rule, another example of quad function. Okay, again, like more examples you see here, like here, this is our function handle, right? And we want to take the integral of this function, sine of x over x, from 0 to pi. And here we want to take the integral of 1 over root 1 plus x raised to power 4 from 0 to 1. And like again, more examples. I'm not gonna solve them, but these are for your practice. More examples here. Okay, another example here, we want to find that this integral, this is a very important function, error function in math, in like many applications, like it's used. So like if you want to find this numerically, then again you can use the quad function to do that, right? And here, like it's asking you to basically see the impact of increasing your intervals, sub-intervals. Like what's gonna happen, like if you have 10 intervals, sub-intervals, or 100, like what happens if you reduce the amount of h, right? So here you see that, like let's say here, when we use trapezoidal rule, our time step is 0.01, right? As you make this step smaller, your answer gets more accurate. So here, like you want to investigate that. What's the impact of h, our time sample, on the amount of error that we get? Another function from MATLAB, it's specific to polynomials. So you can find the integral of a polynomial. How do we represent a polynomial in MATLAB? By just a vector of coefficients. So if this is the polynomial that we want to take the integral of, first we have to provide the vector of coefficients 12, 9, 8, 5, right? And also, you know that like if you take the integral of this one, right? Like here, this is like, it's not like the integral over a certain bound, right? It's basically the antiderivative. So here we want to find the antiderivative of this one. If you want to find the antiderivative, like you know that like we have a constant. So like you can also provide the constant value of your integral. Right, so this is going to be basically taking the integral of this polynomial, right? And it's going to have this constant at the end. Another example here, you see that the application of polyint. Another function that actually has multiple applications, but its application for polynomials, it would be just basically if we have these two polynomials and we want to find what is p times v, right? Like what is the polynomial, what is the vector of coefficients for the polynomial that is p times v, we can use the convolution function, right? It has like many other applications. This is only specific to polynomials, right? And then take the poly integer. Okay, we see that like similar to polyint, we also have diff function for differentiation, which we're gonna see in the next part of this video. This part is for your information, but we can also do double integrals, right? So if I have like multivariable calculus and like we want to take the integral of this one first versus like x, then versus y, then you can provide the function and the two limits for each integral and then use the double quad function to do that, to take the integral, or even triple quad, right? So like if you have like three variables and you want to take the integral first, like with respect to like one of the variables, then another one, then another one. You provide all the limits and you take the integral, and this should give you the answer. One concept that you should be familiar with is that I mentioned that the step size is not necessarily always the same, right? Here we assume that like here, like in all the examples that we did, right, the step size here is, for example, 1. The step size here is 0.01. It's always the same for all the subintervals. But in many practical, real applications, right, we don't want to choose the same step size, right? Sometimes our function changes very fast. So in those circumstances, we want the step size to be very small. In some cases, like at some times, the function doesn't change that much, right? So if that's the case, right, if function changes very slowly, there's no need to have a small step, because like you need to do more calculation, right? It's gonna put a lot of calculation on burden on your software or on your program. So what we have in real life is like something called adaptive quadrature, right? Basically, changing the step size or time sample according to the rate of the change of the function. If our function changes very fast, we want to make the step size smaller, right? So it's similar to, let's say, like if you go to gross grind, like if the slope is very steep, right, the steps are going to be closer to each other, right? If it's not, then like we don't need even like have any steps, right? We just like it's going to be a very flat line, like we just walk on it, right? So that's similar to this concept, and there is a function in MATLAB that would apply adaptive quadrature, like it's called integral, right? Similar to quad, it needs to have a function handle and the limits that you want to take the integral of, right? So like these are like it's like its application, like the way we use it, it's very similar to the way that we use the quad function. So you see some examples of integral function in this slide. Let's continue with differentiation in another video. Thank you so much. Stay tuned for the next video.